Components of a vector. Remember, a vector's got magnitude and direction. We can see this from this plane here, that it's got a velocity vector pointing up theta degrees from the horizontal, and that's the velocity vector here. Now, more often than not, we want to be able to break down that vector into what we call a horizontal component and into a vertical component. This makes calculations much easier when we deal with more complicated problems in physics. Now, to find the horizontal component and the vertical component, we just simply make up a little triangle with the velocity vector. And I'll bring this dotted line over here, and that's a little triangle there. You can see that we've got a right angle in here, and what this line along here represents would be the horizontal component vector, and that would fit snugly in there like that. The vertical vector would look like this one. So that's us got our component, our velocity component, broken down into what we call a horizontal component, which we'll write as VH, and a vertical component, which we shall write as VV. So there's your velocity vector here, V, broken down into a horizontal component and into a vertical component, and it's that easy done. But we want to find the relationship between the velocity vector's magnitude and VH and VV, the horizontal and the vertical component. And to do that, we have to rely on some trig. So to do some trig, first of all, we know that's going to be a right-angled triangle. And we know that opposite right-angled triangles we call the hypotenuse. So we'll put in the label hypotenuse there. We know across from the angle is always called the opposite side of the triangle. And of course the bit left out is called the adjacent side, always between the angle and the right angle. So that's us labelled our triangle. Now to find the values of the horizontal component and the vertical component. If we take sine theta first of all, we have sine theta is equal to the opposite over the hypotenuse. We know that from our trig laws, that sine theta is going to go to the opposite side of the triangle divided by the hypotenuse side of the triangle. So therefore sine theta in this case is going to be equal to the opposite, which is VV, the vertical component, which is what we're after, divided by the hypotenuse, which is V. So we bit rearranging and we get the vertical component VV is equal to V times sine theta. So it's V times sine of theta. And there is our relationship between the size of the velocity vector V and its vertical component size. So this arrow in here, this vector in here, will have a size of V times sine theta. You've broken down the velocity vector into one of its components. What about the other one? Well, much the same. We do know that cos of theta, change colour here, we know that cos of theta is always equal to the adjacent side of the triangle divided by the hypotenuse. So we know then that cos theta, is going to equal to the adjacent side, which is VH, the horizontal component, VH, divided by the size of V itself, the hypotenuse V. And therefore, we cross multiply, we get the vertical component size, VH, is equal to V cos of theta. So there's our second component. So we can easily now break these components, the velocity component, the velocity vector, into its components. So if you've got a vector V at an angle theta to horizontal, then you can see that the vertical velocity component is going to be equal to V sine theta, and the horizontal component is going to be V cos theta. I'll tell you a wee quick way to remember that. If you want to find the vertical component, it's always in the air, in. So we use sine. If we want to find the horizontal component, it's on the ground. On the ground, it's going to be the O on the ground. That's a quick way to remember it, but stick to your triangle to work out the components of the vectors. Now here's a case we have a force vector, which is a frog pushing off from its legs with a force of 50 newtons at an angle of 30 degrees to horizontal. And our job in physics would be to make sure we have the horizontal and the vertical components of that force. Well, we know what to do now. We just complete the little triangle. and that's the little triangle there. You can see we've got 50 newtons for the size of the vector we're looking at, and the angle 30 degrees. So the horizontal component can be represented by that vector there, which lies along the horizontal, and the vertical component can be fitted in there. The blue line represents the vertical component of the force. We can mark them in terms of symbols. We can say this is the horizontal force, so we call that FH, and this will be the vertical force, which we can call FV. There they have the two different colours here. Now, we already know from a previous example that it's quite simple to work out what the size of this vertical velocity one is going to be. The size of it is going to be just simply equal to the size of the vector, which it makes up, 50 newtons, multiplied by, and because it's in the air, it's going to be sine of 30. The vertical vector is always given by sine 30. And we do know that sine 30 is a half, so the size of the vertical component of the 50 newtons force is going to be just simply 25 newtons. And that's the size of that particular vector, 25 newtons in the vertical direction. What about the horizontal component then? Well, we know that the horizontal component is going to be given by this formula. Horizontal component is the size of the vector, 50 newtons, which we're looking at to break down, multiplied by, and it's on the ground, cos of 30 degrees. So we work that out, we get an answer of 43 newtons. So there is our two horizontal and vertical components of that vector, the size of them. So we've got a 50 newton vector at an angle of 30 degrees, and we've broken it down to a horizontal component, FH, which has a size of 43 newtons, and a vertical component, which is a size of 25 newtons. And that's very helpful when we come to different problems, breaking down the 50 newton vector into its horizontal and vertical components. And here's a third example of breaking a vector into its components. We have a young boy in a cart being pulled along by his dad with a force of 70 newtons at an angle of 45 degrees to the horizontal. We'll draw a little sketch of that. So there's the force which the gentleman is pulling his son with. It's got a value of 70 newtons. And horizontally is going to be an angle of 45 degrees to horizontal. So it's our job to break that 70 newton vector into its horizontal and vertical components. And to do that, we just simply construct a little triangle again. There you go there. And we know that the bottom part is going to be the horizontal part, represented by green, and the blue vector represented by the vertical part, like that. And it's quite simple after that, because we know our sine and our cos, and we can write down right away that we have, for the vertical component of this force, we can say the force in the vertical direction, Fv, is going to go to 70 newtons multiplied by, and it's sine, because it's in the air, sine of 45 degrees. You can do that once again with the triangle to make sure we have got that. If you can't remember the little rule of thumb, because it's in the air, we put in sine. So we can work that out then. Fv is going to give you 70 times sine 45, and the answer is 49.5 newtons. We can put that to one significant figure and call it 50 newtons. What about the horizontal component? Well, the horizontal component is found in the same way. The horizontal component, FH, and we know that FH, the size of the horizontal component, is found by saying 70 newtons multiplied by cos of 45 degrees. And we get 70 times cos 45, and we get 49.5 degrees, 45.9 newtons again. And we can, of course, put that into one significant figure by calling it 50 newtons. So do you notice then we have a diagram here which is not to scale, but if you've got a force at an angle of 45 degrees to it, then the horizontal component and the vertical component are going to be exactly equal, 50 newtons and 50 newtons. So that's examples how we break down a vector into its component form, which helps us do physics calculations which are much harder.